Hi, I'm Mr. True. In this video and a few that are going to follow, we're going to start looking at vectors, where we have this geometric shape, which is a ray, and we use that to display the strength and direction of forces. I do teach pre-calculus, so we're not going to go real in depth with these, not like you would be, say, if you were in a physics class, but hopefully we'll give you a nice understanding of the basic structure of vectors and some of their more fundamental uses. Now, a vector is a ray, and it displays the direction and the amount of force in just the physical world. So if you're in an area like I live in that is, has hurricanes or just some tropical storms, and of course you get tornadoes and whatnot, but it seems like every time we're into hurricane season, our weather channels, anytime a big storm shows up, likes to put these wind maps on the screen, and it's just covered with arrows. Each one of those arrows representing the speed and direction of the wind, which means that each one of those arrows is an example of vectors. Another example of vectors is, I've got this rectangular object here. It weighs supposedly 10 pounds. Of course, I just made that up. And just say it's a picture frame. And we're hanging that picture frame with a couple of wires. What scenario, white, red, green, or purple, do you think would be most efficient way of placing those cables to hang this picture frame? Well, that would be vertical. If this entire frame is 10 pounds, then each of these vertical vectors in the opposite direction of gravity, which pulls down, will give you the most efficient way of hanging that picture, or to put the least amount of tension on those wires. Now, if I start to let those wires kind of fan out and maybe use this orientation, the purple lines, to hang the 10-pound picture frame, then how much force would be placed on those cables? Do you still think that it would be 5 pounds? Because it's being shared evenly from the left and right-hand side. Well, actually, the answer to that question is going to be no. We're not going to answer that question in this video. We're just building up the basic structure of vectors and learning all the concepts and the vocab. But in the next video of application of vectors, we will learn that question of, well, if you have a 10-pound item, you have some vectors in some kind of given amount of angle. I'm out of colors here. Where we have some sort of fixed value of theta. Knowing that there's a vertical pull of 5 pounds on this side of the picture with gravity, and knowing that there's some kind of given angle, what tension is actually on that cable, I will tell you that it's going to be a lot more than 5 pounds. The more you let those cables fan out, the more you're wasting energy in the horizontal direction, and less energy is being placed in the vertical direction to oppose the gravitational force. So, I'm just trying to give you a purpose, an idea of what vectors are for and how they're going to be used. This kind of question of finding forces in different directions is what we're going to look at later when we do applications. But for now, let's get the basics done. Okay, a vector is a ray, like I stated. It has an initial point labeled as x sub 1, y sub 1, and a terminal point labeled as x sub 2, y sub 2. It has a length which describes the magnitude or the amount of force that vector is applying. When you have this sort of like double absolute value symbol, in vector language that means magnitude. So when you see a vector, and when you label a vector, it's simply going to be usually a single letter, and you get this little ray symbol, the same thing you would have done in geometry when you first started learning how to display line segments and lines and rays. A vector is a ray, so you'll have the same kind of little notation or little sideways arrow above a variable, and that's going to be an indication that's a vector. So this double line symbol around a vector name means you want the magnitude or its length. You're going to have an angle of rotation which describes the direction of the vector, and I'm not drawing an initial side. If you've been watching all my videos or if you've been studying trig recently, you know that when we draw angles, we have an initial side and a terminal side. I don't want to draw the initial side because I don't want you to think I'm drawing an angle. I'm drawing a vector. But that direction is going to be the same as we describe rotations in trig, where it's a standard position rotation, where you start at the positive x-axis and you rotate counterclockwise to indicate a positive direction. And we do like vectors to be described in terms of magnitude and direction. Now, if I go back to the example of wind, we don't measure wind in standard position rotation. We measure wind as far as like bearings. Is it north? Is it east? Is it northeast? And you want to say the wind is blowing in the northeastern direction at 20 miles an hour. So vectors, and when you're describing them to people, we want to really hear how much force or speed is being applied and what direction is it in. But working with magnitude and direction, working with it mathematically is not easy at all. So most of this discussion is going to be vectors in terms of x and y components, or horizontal and vertical components. You'll see that as we get through here. Our first example of drawing a vector is I have a vector whose magnitude, is equal to 2, and its rotation or its direction is 30 degrees. Well, vector v would look like this, roughly, of course. Now, this vector has a length of 2, and its direction is in the direction of 30 degrees. Now, here's a little preview of actually the very last example I'm going to do. This vector has a direction of 30 degrees and a magnitude or length of 2. How would we describe that in terms of its horizontal and vertical components? And I'm getting ahead of myself a little bit here, but if you've been studying trig and studying the unit circle quite a bit, you should actually know right off the top of your head how much is the horizontal component and how much the vertical component is, because you should understand or know the sides of a 60-30 triangle. That looks like 130, but that's paint on my board. Sorry about that. So this is a 60-30 triangle. What are the sides? What are the ratio of the sides of a 60-30 triangle? If it's been so long since you've thought of that, maybe you might know what the sine of 30 degrees is. The sine of 30, which is opposite over hypotenuse, is 1 over 2. Now, okay, that worked. What's the cosine of 30? The cosine of 30 degrees off the unit circle is square root of 3 over 2. So either you remember that a 60-30 triangle has got the ratio, the sides and the ratios of 1, 2, square root of 3, or if you maybe have forgotten that, since this angle is off of the unit circle, we came up with it another way. But at any rate, for a 60-30 triangle, our sides are 1, 2, square root of 3. And I did kind of hint as to what's coming by talking about sine and cosine. So this vector with this magnitude and this direction can be described in two ways. It could be described as square root of 3 I plus 1j, and I'll describe later what that little I vector and j vector are. Or, my new pre-calculus book doesn't use these notations, but my old trigonometry book that I taught it for quite a few years did. It would describe this vector in terms of this, square root of 3, comma, 1. And it would use some pointy parentheses, if you will, to describe that horizontal and vertical component. So I did a lot of babbling to try and explain why you want to learn about vectors. Let's pick up the pace a little bit and get through all these basic vocab and, concepts for you. Two vectors, or two definitions here. Equal vector and opposite vectors. Equal vectors have equal lengths and the same direction. So I've got a couple of examples drawn up here, vector v and vector w. They have the same length and same direction. In other words, they're parallel. We don't normally talk about being parallel with vectors, but that's, they appear to be parallel. They're going in the same direction, and indeed they are. But of course, with vectors, we're normally describing direction with a rotation angle or a theta angle. Opposite vectors are, again, equal in length, but they have opposite directions. So I've got two vectors drawn. They are going in the same direction. If you were to look at the initial and terminal points and find slope, you would get the same slope for both of those vectors. They're parallel. But again, that's not how we describe the direction of vectors. We describe it with rotation. So while this vector is at an angle of 40 degrees, a vector in an opposite direction would need to have an angle measure that is separated by 180 degrees, or pi. Because of course, if I'm looking in one direction and I want to go in the opposite direction, I have to rotate, 180 degrees. So if this has got a direction of 40 degrees, then an opposite vector would have to have an angle of rotation, or directional angle, that is separated by pi, or 180 degrees. So, opposite vectors. Now, I am teaching out of a pre-calculus book. This is not physics, so we only do vectors for 2 sections. When I used a proper trigonometry book, there was a bit more, and I'll do more videos like that approach those problems as well. There was more work done with vectors in their design where you talk about direction and strength. But it really is much, much easier to work with vectors in terms of their x and y components. And my new textbook definitely does a lot more of that than my older trigonometry book did. So that's going to be the main idea behind all these examples and concepts we talk for the rest of this video, is vectors in terms of their x and y components. So let's figure that out. Or vectorize a horizontal component with a vector length of 1. So I is simply a horizontal vector with a length of 1. J is a vertical component vector with as well a length of 1. They're called component vectors, thus their lengths are 1. I is horizontal, J is vertical. So vector V equals A times vector I plus B times vector J. I'm just going to start saying this, AI plus BJ, vector J. That is equal to x sub 2 minus x sub 1 times the I component vector plus y sub 2 minus, y sub 1 times the vector component of J. And this idea of naming or coming up with a vector in its horizontal and vertical components is, of course, if you're given an initial and terminal point, which we're going to work out this example in a second. The magnitude of a vector is equal to the square root of x sub 2 minus x sub 1 plus y sub 2 squared plus y sub 2 minus y sub 1 squared. Of course, this is just the distance formula because, well, I'm being given an initial point and a terminal point. So, of course, if I'm going to find magnitude or length with the same old formula I've been using now for many, many years. So, given this initial and terminal point, that means that this is considered x sub 1, y sub 1, and x sub 2, y sub 2. So vector V is going to be equal to x sub 2, which is 5, minus x sub 1, which is negative 3, with the I vector, plus y sub 2, which is 11, minus y sub 1, which is a 4. Times the component vector J. And that comes out to be, well, anytime you have two negatives next to each other, they cancel out. So it's going to be 5 plus 3, which is 8. So 8i plus 11 minus 4, which is 7j. Now, this is pretty much how my book sticks with the vector notations, and it really sticks to that I and J notation. My older textbook, my trigonometry book that I used to teach out of, was a lot nicer to simply say that given this initial point and this terminal point, that this vector is going to be labeled 8, 7. Now that looks like I'm naming a coordinate, but you'll notice that the parentheses are actually pointy parentheses. Round parentheses indicates that you're labeling a point, just a coordinate. The pointy brackets is vector notation, and that is a difference. We are going to be, plotting this vector of 8, 7. It will be displayed as a ray, and when you plot vectors, we're going to do this in a second, but when you plot vectors, you can put the initial point anywhere you like. When you're plotting a coordinate, of course, you always have to start from the origin. What is the magnitude of this vector? Now, that is the distance formula. and I have 2 points given to me. But now that, now that I've already found, this sort of condensed name or version of the vector, where I've written it in its horizontal and vertical components, we might want to remember that the distance formula is derived from the Pythagorean theorem. So while this is the version of magnitude that my textbook uses in its notes, we might want to remember, especially when you have a vector already in its component form, that you can simply say, whether I look here or I look here, A times vector I plus B times vector j, that the magnitude of a vector is also simply the square root of A squared plus B squared, which is basically just Pythagorean. It is Pythagorean theorem. That's how we derive the distance formulas from the Pythagorean theorem. So the magnitude of vector V is the square root of 8 squared plus 7 squared, which is the square root of 64 plus 49, which is the square root of 113. But I'm out of space, and I'm sure you know how to find the distance formula. So that is equal vectors, opposite vectors, and finding or describing the vector in terms of its horizontal and vertical components, given your initial point and your terminal point. Let's do some more. Alrighty then, let's do a quick sketch and find some magnitude. Vector V is equal to 5i plus 3j. We're going to sketch it and find its magnitude. Now again, if your book is using this notation, you might see that vector V is displayed as 5, 3. I like this much better for notation, but I got to stick with the notation my book is using so I don't confuse my kids. Vector V, 5, 3. Now, I could just pick a point. I'm going to do the origin, because it's familiar, and go over 5, 1, 2, 3, 4, 5, and up 3. So, there's vector V. But with vectors, unlike plotting a coordinate, you can put them anywhere. So I could have started, let's say, here at 2, negative 3, and gone over 5. So 1, 2, 3, 4, 5, and up 3. Well, that's vector V as well. I didn't rename it, so I'm not going to call them equal vectors, though they are, but I'm displaying them both as vector V. So with vectors, you can place them anywhere you like. Unlike a coordinate. If I said, probably should have done that on the origin. If I said plot 5, 3, then that would simply be a point on 5, 3. It would not represent an array, and it would certainly have to be plotted starting from the origin. Now finding its magnitude is, again, the distance formula, square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared, or remembering that the distance formula just comes from the Pythagorean theorem, we can just simply say, well, this is 5, this is 3, so the magnitude of V is again the square root of 5 squared plus 3 squared, which is the square root of 25 plus 9, or 34. Scalar multiplication increases or decreases the length of a vector. So, if I say I want 2 times vector V, then, well, it says if I want to do a scalar multiple of a vector, I do k times A and k times B. So, I'm just going to take 2 times 5, my A value, or I can do it with just here, I plus 2 times 3 times vector j, my horizontal and vertical component, and my answer is 10I plus 6 vector j, or 6j. And what does that do? Well, if I start from here again, instead of going over 5 and up 3, I'm going to go over 10. So 5, 6, 7, 8, 9, 10, and up 6. So 1, 2, 3, 4, 5, 6. And all I'm doing, as you would expect, is making my vector, in this case, because my scalar multiple is 2, I'm just simply making my vector twice as long. And you know, when we talk about forces, certainly, you know, wind can pick up and double its speed. I can push harder on something, twice as hard to make it, you know, try and get it to start moving. So, you know, scalar multiples are just simply increasing or decreasing these natural forces that we have that we're trying to represent with our vectors. Bam! Now, in life, we generally have more than just one force acting on an object. So it is very important for us to be able to find and display resultant vectors. You know, we're going to add and subtract vectors. We're going to combine forces on, you know, from many directions on maybe like an object to get it to move or stay stationary. So we need to come up with an idea or a way of showing this addition or subtraction of vectors both graphically or just simply with drawing and working with the horizontal components and the vertical components. So I got a couple of vectors drawn here. It's A and B. I've only got 2. And there's 2 ways to draw the resultant vector. Like, say we're going to add or subtract these vectors. One is the parallelogram rule, and one is, I wish I had a name for it. If there is one, I don't know what it is. End to end, I like to call it the triangulate, sort of like the triangle method. That's not really very good though, because if you have more than 2 vectors, you're not going to really draw a triangle. But at any rate, if I want to say let's draw vector A plus vector B. Well, if I'm doing the parallelogram rule, that means I'm going to start both vectors at the same initial point. So there's a point. Here is, as best I can estimate it, vector A. Here is vector B. And the resultant is going to be drawn through the parallelogram that I can make with those 2 sides. So just the best I can here, try and get a reasonable representation of a parallelogram. And then from, you know, I'm going to draw a diagonal through that parallelogram, and that diagonal is going to be my resultant vector, or vector A plus vector B. Well, okay, what if I wanted to do vector B minus vector A? Well, vector B, let's go ahead and draw that first from an initial point. So, somewhere around like that. Vector A, it says minus vector A. Now that means that we're going to go in the opposite direction. It's an opposite vector. It's negative A instead of positive A. So instead of drawing A out in this direction, I'm going to draw it in the opposite direction and at the same length, and let this represent negative A, or the opposite of vector A. I think I did forget to do the little negative sign on the opposite vectors I just talked about a minute ago. And then we're going to draw a parallelogram and draw a diagonal through that parallelogram, and that's going to be my resultant. Now, a couple of things. I could be talking about, maybe I should, do a scalar multiple, but one restriction or one thing I don't like about the parallelogram method is if you have more than just 2 forces working on the same, or working together, if you're trying to find the resultant of more than just 2 vectors, I find personally using the parallelogram rule rather difficult, because how are you going to draw a parallelogram when you have 3 or 4 vectors working together on this particular force or this object? If you want to find the resultant of more than just 2 vectors, that's going to be a bit of an issue. So what if I wanted to draw the representation of, instead of B minus A, vector B minus vector A, I want to do 1/2 vector B minus a. I want to apply a scalar multiple of 1/2. Well, that's going to take vector b and simply shrink it in half. Cut its magnitude or its length down by 1/2. And again, parallelogram and draw your diagonal as your resultant. Okay, now I do prefer, though, instead of the parallelogram method, to draw them end to end. So in other words, I want to make, let's see, how about 3a plus vector b. Well, 3a plus vector b is going to be take vector a, there's no negative in front of it, so we're going to keep it in the same direction, just make it 3 times as long. So here's 1 length of a, 2 length of a, and there is, the best as I can sketch, 3a. And then, instead of drawing b starting from the same point, I'm going to go end to end and start b up here. So vector b is somewhere around that length. Now, if I wanted to add now a third vector and say, well, there's vector c. Instead of just doing 3a plus b, I want to do vector 3 times vector a plus b plus vector c. And with this end-to-end method, I can just go, well, there's 3 times a, there's 3a, there's b, and here is vector c. I'm going to go back to my initial point, draw straight to my final terminal point, and maybe try and do a straight line, but whatever. That comes out to be this right here. This purple vector is 3a plus b plus c. Let's not forget this is a scalar multiple, and this is the resultant vector. So there is my preferred method of drawing vectors in space. That's using, let's just call it the end-to-end method, as opposed to the parallelogram method. Working with horizontal and vertical components. If you want to add vectors or subtract them, all you have to do is add the horizontal components and or subtract them, and then add or subtract the vertical components. And really it's pretty straightforward. So we got vector v, it's minus 2i plus 7j. Vector w is minus 3i minus 2j. And you can see those again with those pointy brackets, but I'm using the ij notation because my book does. I really prefer the shorthand version of this, but whatever. Find 2w plus 3v. So we're going to do a scalar multiple on w, so it's going to, of 2. So it's going to be 2 times negative 2i plus 7j plus 3 times vector v. Oh, I just got that backwards, didn't I? Let's try that again. 2 times vector w, so it's going to be 2 times vector w, negative 3i minus 2j, plus 3 times v, so 3 times negative 2i plus 7j. That comes out to be, and you just distribute through the parentheses. So 2 times negative 3 is negative 6. 2 times negative 2 is negative 4. And then plus, positive 3 times negative 2 is negative 6i. And 3 times 7 is 21j. And this will have a resultant vector of, let's see, I'm going to add the horizontal component, so negative 6 and negative 6 is negative 12i, vector I. And negative 4j plus 21j is 17j. And so this is how you add or subtract vectors and do scalar multiples with simple drawings, going end to end. And this is an example of combining scalar multiples and adding and subtracting vectors in terms of their horizontal and vertical components. A couple more screens and we're almost done. Thank you for watching. I do greatly appreciate it. We do have something called a zero vector. It's a vector with a basically horizontal component of 0 and a vertical component of 0. So it's really just a point as opposed to an array. So it doesn't seem to be like really all that necessary, but we will be talking about zero vectors when we do applications of vectors and talk about items that are in equilibrium or in a static state. That's where all the forces are, basically balancing each other out so that the object is not in motion at all. Think of, say, like a picture frame hanging on a wall. It's stagnant because the wires are balancing out the forces of gravity and keeping that item steady. If you need to take a vector and shrink its length to 1, and you will need to do that in some of the later formulas that we're going to use, not in this video, but we will need to be able to take and find unit vectors. So finding a unit vector is a vector with a length of 1 and the same direction of a given angle. So in other words, we're just going to take a vector and shrink it, whatever its length is, shrink it to a length of 1. And that'll be used in later formulas. So this is just vector v divided by its own magnitude, which you can think of as kind of like scalar multiple. Like instead of dividing by 5, we'll be multiplying by 1 over 5. So really kind of no big deal. Here's an example. We have a vector with a horizontal component, or vector negative 3i minus 4j, or negative 3, negative 4. And we want to write a vector that has the same direction but has a length of 1. So we're going to find the magnitude of this vector. So the magnitude of v is going to be the square root of a squared plus b squared, which is going to be the square root of 9 plus 16, which is 25, which is equal to 5. So what we're going to do is, I'm going to take this vector, I'm going to basically just divide it by the magnitude that I just found was 5, and write my final answer as negative 3/5 I minus 4/5 j. Or you might see the same type of notation in the shorthand form without the i's and j's. One last example. Bam! Now, vectors are nice when you want to, or naming vectors in terms of magnitude and direction is nice, but those numbers are not friendly to work with. So we want to talk about vectors in terms of direction and strength, but we want to work with mainly vectors in terms of their x and y components. We want to make sure we can convert back and forth. We've got a little diagram set up here, and let's from that diagram come up with some formulas that actually we already know. Vector v is a times vector I plus b times vector j. I've got it drawn with its initial sign on the origin, just for convenience sake, doesn't need to be. I've got it drawn in quadrant 2, but I'm not going to crunch any numbers, so I'm not worried about signs. And let's just look at the cosine of theta. Now the cosine of theta is adjacent over hypotenuse. Since I've put my initial sign on the origin, you can think of it as x over r. We need to lose that r idea because vectors don't have to be placed on the origin, and thus r, radius of a circle, kind of loses its meaning a little bit. So the cosine of theta is going to be a over the magnitude of v, which is just simply a length, remember? Thus a, the coefficient of the horizontal component, is going to be equal to the magnitude of v, again, which is just a length, times the cosine of theta. If you kind of just squint and lose all that vector notation stuff, this is the same cosine as adjacent over hypotenuse, sines y of opposite over hypotenuse, that you've been using now for a couple years, if not at least a few chapters since you've been going through trigonometry. The sine of theta is opposite over hypotenuse, so it's going to be b over the magnitude of vector v, which is just kind of like the hypotenuse of the triangle I've drawn here. And that means that b is going to be equal to the magnitude of v times the sine of theta. And we have a vector again that is in component form a I plus b times component j. And incorporating this idea, that's equal to the magnitude of v times the cosine of theta plus, with the I, plus b, which is now going to be the magnitude of vector v times the sine of theta j. Okay, let's actually put these into practice. Our example, vector v has a magnitude of 4 and a direction of 30 degrees. So let's just kind of sketch this out. Looks something like this. There's vector v, and there is a direction of 30 degrees. Now, from that magnitude and direction, now let's go ahead and write that down. The magnitude of v is equal to 4. So from that magnitude and that direction, I want to find the horizontal and vertical components, which means I need to make a little right triangle out of that. And how do I find this little horizontal component of A? I'm going to just do this like from trig that we understand and not just really directly use this, to be honest. A is going to be equal to, well, let's see, adjacent hypotenuse, so the cosine of 30 is going to be equal to A over the magnitude of 4. A is going to be equal to 4 times the cosine of 30. And what is the cosine of 30? It's square root of 3 over 2. So this is going to be 4 times the cosine of 30, which is square root of 3 over 2. And 4 divided by 2 is 2 square root of 3, right? The vertical component of b is going to be found through sine, so the sine of 30 is equal to b over the magnitude of the vector of 4, so b is going to be equal to 4 times the sine of 30, and the sine of 30 is equal to 1/2, and half of 4 is equal to 2. Now, you might also note that I've drawn a 60-30 triangle, and if you remember your ratios of a 60-30 triangle, they are what make up the unit circle after all anyway. Is a opposite 30 is 1, hypotenuse is twice as long, and the side opposite 60 is square root of 3, so 1, 2 square root of 3, or x, 2x, x square root of 3. So we could have just simply said, from our knowledge of specialty triangles, that this side is 2 and this side is square root of 3. And honestly, we could have answered this question without even using trig functions, but the point is to show you how all this works. So, that all being said, this vector with the magnitude of 4 and a direction of 30 degrees can be described as 2 square root of 3 I, if you're using those silly component form things, plus 2j. Or, as I would prefer to write, if my textbook used this notation more, 2 square root of 3, comma 2. Okay, last example. Write v equals negative 3i minus 3j in terms of magnitude and direction. So I want to go in the opposite direction. Sounds like it might be new, we're learning vectors, but we've been doing this now for like 3 chapters. Our vector, and I'm going to again, for convenience sake, put the initial side on the origin, has a horizontal component of negative 3, a vertical component of negative 3. Here is my vector v. I want to describe that in terms of magnitude and direction. Well, how long have you been seeing me do this now? A little right triangle. We've got a side of negative 3, another side of negative 3, We're going to find the magnitude of the vector by doing basically Pythagorean theorem, or exactly. The magnitude of v is equal to the square root of negative 3 squared plus negative 3 squared, which is the square root of 18, which is the square root of 9 times 2, which is 3 square root of 2. So now we have the magnitude. What about direction? Man, how long have we been finding standard rotation angles? And again, if you put that for convenience sake, the initial side on the origin, that's really familiar looking. The tangent of theta is, well, it was y over x. Then with polar form it became b over a. And since b is again our vertical component and a is again our horizontal component, the tangent of theta is again going to be b over a, or negative 3 over negative 3, and in this case that's equal to 1. Now you should know that that's going to be 225 degrees, or 1, 2, 3, 4, 5 pi over 4, but in case you're still using your calculator for this, inverse tangent of 1 is going to give you an answer of 45 degrees, which is not the answer but a usable number because our calculator is just limited on how it can give us inverse, do inverse trig functions. And with inverse tangent again, negative 90 to positive 90. So this is not really our answer. We really need 180 because we just passed it plus 45 degrees. So our final answer from going from horizontal and vertical components into magnitude and direction is going to be vector v has a magnitude of 9 square root of 2, 3 square root of 2, and a direction of 225 degrees, or 5 pi over 4 radians. Woo! I'm Mr. Tarrou. Bam! Go do your homework.